Somewhere in New York, at the Simons Foundation, there is a laptop. Not a supercomputer, not a room full of dilution refrigerators cooled down to a hair above absolute zero. Just an ordinary laptop running open source code. And in May of 2026, that laptop did something that a company called D-Wave had publicly said in one of the most prestigious journals in science was basically impossible for any classical computer to do. So yeah, this is one of those stories where the machine that was supposed to lose ends up quietly stealing the show. But before we get to the laptop, we have to talk about the thing it was competing against, because D-Wave's original claim was a pretty big deal when it came out. In March of 2025, in the journal Science, a team working with D-Wave's Advantage 2 system, a quantum annealer packing about 5,000 qubits, announced that they had simulated the dynamics of a disordered quantum system, essentially a tangled, glassy network of interacting particles, and that this simulation had crossed a line, not just fast, not just efficient, actually beyond what any classical computer, no matter how big, could realistically do in a reasonable amount of time. That's the claim that's usually shorthanded as quantum supremacy, or sometimes the slightly more modest phrase, beyond classical computation. And I guess to understand why that claim mattered, we need a super quick refresher on what these quantum machines are actually simulating. Because the object at the center of this whole story is something called a spin glass. Picture a huge grid of tiny magnets, and each one is only allowed to point up or down. In a normal magnet, all those little magnets agree with each other, and you get one big clean field. But in a spin glass, the connections between neighboring magnets are randomized. Some want to align, some want to oppose, and the whole system gets frustrated. It can't settle into one obvious answer. Instead, it freezes into a messy, disordered pattern that depends sensitively on its exact history. Now do that with quantum particles instead of classical magnets, where each one can be in a superposition of up and down at the same time, and let hundreds of them interact on a three-dimensional lattice, cubic, diamond, whatever shape you like, and you get a system whose full mathematical description balloons exponentially with every particle you add. 2 qubits, 4 possible states. 10 qubits, over 1,000 states. A few hundred qubits, and the number of variables you'd need to track on paper exceeds the number of atoms in the observable universe. That's basically the whole pitch for quantum computers in the first place. That nature seems to solve this bookkeeping problem for free just by existing as a quantum system while our classical computers choke on it. So when D-Wave's team ran their annealer through this spin glass problem and got results that lined up with theoretical predictions of something called Kibble-Zurich physics, essentially how fast defects freeze into a system as it's rapidly cooled, and when they said their classical comparisons all fell short, that was a legitimately exciting result. It's the kind of thing that gets headlines like "Quantum Computer Does the Impossible." And for a while, that was more or less the accepted story. But here's where things get just a little bit stranger, because sitting in an office at the Flatiron Institute's Center for Computational Quantum Physics was a physicist named Joseph Tyndall, and he had a hunch that the classical comparisons in that original paper hadn't actually exhausted what classical methods could do. And that's because Tyndall and his colleagues, Antonio Francesco Mello, Matthew Fishman, E. Miles Staudenmeier, and Dries Sells at Boston University had been quietly building up a different kind of classical toolkit for exactly this sort of problem. It's built around something called tensor-networks, which is a mathematical trick for compressing an enormous quantum wave function into something that fits on a laptop, sort of the way a zip file compresses a giant text document without losing the information inside it, at least approximately. Tyndall himself apparently described it in almost exactly those terms, a zip file for the wave function. And the compression only works well if you can keep track of which parts of the system are entangled with which other parts, because entanglement is basically what makes quantum description so bulky in the first place, which is where the second piece comes in, and honestly, this is my favorite detail in the whole story. The technique they use to manage that entanglement, called belief propagation, is not new. It's not some cutting-edge 2026 invention. It was first developed back in 1982. originally as a method in classical statistics and computer science for reasoning about uncertain, interconnected systems, things like error correcting codes or probabilistic graphs. Nobody built it with quantum spin glasses in mind. But it turns out that this decades old message passing algorithm, adapted and combined with three-dimensional tensor networks and a piece of software called iTensor, is really, really good at propagating just enough information across a lattice to keep the compression accurate without needing to track the full exponential mess. And so, using this combination, mostly built and tested as it happens on an ordinary laptop, the Flatiron and Boston University team went back to the exact spin glass problem D-Wave had claimed was beyond classical reach, and they simulated it. Square lattices, cubic lattices, diamond lattices, systems with hundreds of interacting qubits, and their results scaled roughly linearly with system size rather than exploding exponentially. In the case of the dimerized cubic lattice specifically, their errors came out comparable to the errors in D-Wave's own quantum hardware. Not close in spirit, comparable in actual accuracy. Their paper, Dynamics of Disordered Quantum Systems with 2- and 3-Dimensional Tensor Networks, was published in Science on May 21st, 2026, which, if you're keeping track, is the same journal that ran the original Beyond Classical claim just 14 months earlier. Now, obviously, D-Wave was not thrilled to see headlines saying a laptop had debunked their Supremacy claim, and I think it's worth walking through their response honestly, because this is not a case of a company simply being caught out and staying quiet. D-Wave issued a formal rebuttal within about a week, and it made 4 fairly specific technical points. First, they argued the Flatiron team's belief propagation approach never computed the full state data profiles and certain fourth-order physical observables that D-Wave's own processor produced. So the comparison, in their view, isn't apples to apples. Second, they pointed out that the classical simulations didn't attempt the most complex non-planar biclic lattice geometries from the original paper, only the more tractable square, cubic, and diamond arrangements. And there were 2 more points along similar lines, essentially arguing that the hardest instances and the highest order measurements still haven't been matched classically. D-Wave's official statement put it plainly, that the claim their achievement has been overturned is inaccurate and not supported by the scientific record, while still, to their credit, calling the tensor network advanced genuine progress. So who's actually right here? And I guess the honest answer is, it depends on which slice of the original claim you're looking at. On the specific lattices and observables the Flatiron team tested, the classical laptop method appears to genuinely match the quantum hardware state-of-the-art accuracy, comparable error bars, all achieved with what the researchers themselves called modest computational resources. That part looks pretty solid, but D-Wave's pushback about the hardest, most exotic lattice geometries and the higher order observables is not obviously wrong either. Those specific cases really might still sit beyond what belief propagation and tensor networks can efficiently reach, at least for now. Which means the fair, if slightly less headline-friendly, summary is something like this. A big chunk of what was called Beyond Classical in March of 2025 turned out, 14 months later, to not be Beyond Classical after all. But not necessarily all of it. The goalposts didn't get erased. They got moved to a smaller, more defensible patch of ground. And honestly, this is exactly how this particular corner of physics has worked for years now. Not just with D-Wave. Google's Sycamore processor, IBM's Eagle chip, various photonic boson sampling experiments. They've all made beyond classical claims at one point or another. And in several of those cases, classical algorithms, often tensor network methods very similar to the ones used here, eventually caught up, sometimes within months. There's actually a recent paper arguing the reverse is also possible, that tensor networks with belief propagation cannot feasibly simulate at least one newer Google experiment. So the race really does run in both directions depending on the specific hardware and problem. Wikipedia's own article on quantum supremacy has been updated to note, more or less verbatim, that due to unpredictable, improvements in classical computers and algorithms, quantum supremacy may be temporary or unstable. That's not a throwaway line, that's turning into the actual defining feature of the field, which brings us to the bigger question underneath all of this, the one that doesn't get resolved just because one paper answers another. What does quantum advantage even mean if the classical boundary keeps sliding every time someone builds a cleverer algorithm on cheaper hardware? Every beyond classical claim so far has effectively been a snapshot, a statement about what the best classical methods known right now can and cannot do, not some permanent law about what classical computers can never do. And a laptop running 1980s math just reminded everyone again that the classical side of that boundary has a lot more room left in it than people assumed. So the next time you see a headline about a quantum computer doing something impossible, it might be worth asking, impossible for how long?